Hello everyone, welcome to the sort of math half of the chapter, you might say. If we're going to talk about electrons moving from one atom to another atom through reduction, oxidation, electrochemistry, the difference between them, in other words, the electrical potential of a voltaic cell is a measure of its ability to produce that current. And the way we measure electrical potential, and we talk a lot about this in physics, is volts. The electrical potential results from that electron motion. How strong the competition is between the atoms, or how easily the electrons can flow, and how many electrons are poised to do that transfer is what the electrical potential basically is. So the tendency of a given half reaction to occur as a reduction is a type of electrical potential we call the reduction potential. So how easily it accepts electron is the reduction potential. And the difference between the reduction potential for two half cells is called the cell potential. Now remember, in a cell, or in a half cell, you have oxidation occurring in one half cell and reduction occurring in the other half cell. And when you put the two cells together, then you have a full cell, a voltaic cell, in which electrons go from the oxidation half cell to the reduction half cell. And the cell potential is basically the propensity for reducing of the reduced cell minus the propensity for reducing between the oxidized half cell. Now there is such a thing as oxidation potential, which is the propensity to be oxidized. But here we want to look at the reduction potential of both sides because it is the difference between that reduction potential that tells us the potential of the cell as a whole. So the electrical potential of a cell is the electrical potential or the reduction potential of the reduced side, which is where the electrons are being gained, minus the electrical potential, the reduction potential of the oxidized side, where the electrons are coming from. And I'm going to do several examples, plus I posted a video for this. So how do we find it? Let's go back to our lemon battery, but now we're going to add in the reduction potentials. And these are on page 689 of our text. First of all, the reduction potential of copper. And notice how it's copper 2 plus 2 electrons becomes copper, right? Now that the way it's drawn is gaining electrons reduction. Okay, so copper plus the 2 electrons becomes copper. So that's the reaction that's actually happening for copper. And its reduction potential, according to tables, is 0.34. Now, the zinc side, now that's where oxidation is occurring, but I've written it as a reduction reaction because it's the reduction potential that matters. Now I could write it as an oxidation, and I could use the oxidation potential and add it. So you can add the oxidation potential or you can subtract the reduction potential. And since we're already using reduction potential for the reduced side, we just stick with reduction potentials to make it easier. Everything's in one table. So the reduction potential of zinc is negative 0.76, and I've written it as a reduction, zinc 2 plus 2 electrons coming from the zinc. Notice how the arrow is in the other direction. It's backwards just to show you that the arrow tells you the way the reaction is actually happening, but I've written it as a reduction. So the reduction potential of copper is 0.34, and the reduction potential of zinc is negative 0.76. Because reduction takes place at the copper cell, that is the cathode. Cathode is where the reduction takes place. That's where the electrons are ending. But now to find out the total cell potential, I take the potential of the reduced side, which was the 0.34, minus the potential of the oxidized side, negative 0.76. Minus a negative becomes positive, and I get 1.10. And since that electrical potential is positive, the reaction is spontaneous. So this math will tell you what the potential is, which is basically a measure of how readily available the electricity would be from this reaction. How readily available is this electron transfer happening? But it also tells you whether it will happen or not on its own. If it's a positive value, it's spontaneous. So we want a voltaic cell to have a positive electrical potential. And the electrical potential is the difference in the reduction potentials. Let's look at example 2. Determine the standard cell potential of a voltaic cell, but now we're not doing zinc copper, let's do lithium copper. And notice how I've drawn it so that the electrons go from lithium to copper. So since lithium is first, that's the oxidized side, because that's losing electrons, and copper is gaining electrons, that's where reduction will occur. The reduction potentials from table 23.2 are, for lithium, negative 3.05. And for copper, positive 3.4. Since copper is where the reduction is occurring, we take the copper number minus the lithium number. So I take the electrical potential of the cell is equal to the reduction potential of the reduced side minus the reduction potential of the oxidized side. Now another thing to keep into account here is that lithium goes to lithium plus 1. Copper is coming from copper 2+. So in order to balance the charge, I actually need 2 of those lithium reactions. So I also have to balance the charges when I do the reduction potentials. So I take the reduction potential of copper, 0.34, but I actually subtract 2 times the reduction potential of the lithium side, negative 2 times negative 3.05. I add those together, so I get 6.1 plus 3.34 gives me 6.44. Once again, it is positive, and it is spontaneous because of that, and it's bigger than the zinc value, so there is more potential here. So in this example, I used the shorthand notation in order to inform you where the reduction was and where the oxidation was. And you also had to multiply one of them by 2 so that the charge was balanced. Let's look at another example. Determine the cell reaction, standard cell potential, and which half cell acts as the cathode for the following voltaic cell. So I'm asking you to do everything here. First of all, determine the cell reaction, the standard cell potentials, and which cell acts as the cathode. Basically, we need to figure out which one of these is going to be the anode and which one is going to be the cathode. Where will oxidation occur and where will reduction occur? If I look at those two electrical potentials, those reduction potentials, if I take a positive number minus a negative number, I get a positive number. So I need my cell to be set up so that the positive number is minus the negative number. And remember, we want the reduction potential minus, or the reduction potential of the reduced electrode minus the reduction potential of the oxidized. So since the 0.77 has to come first, that means the 0.77 has to be where reduction is occurring. So iron has to be the reduced substance here, and nickel has to be where oxidation is occurring. So the half cell with the more positive reduction potential is the one in which reduction will occur, the cathode. So iron acts as the cathode and will gain an electron. So iron will be the iron 3+ plus electron yields iron 2+. That will be the reduction reaction, and it is written correctly. Nickel will therefore be oxidized. So nickel will actually have the reverse reaction happen. Nickel will become nickel 2+ plus 2 electrons. So here I have my two reactions written out. Nickel produces nickel 2 plus 2 electrons. But I have to balance those 2 electrons because iron was only giving up 1 electron. So to find the standard cell potential, I have to balance those electrons. I have to multiply the iron side by 2 so that I have 2 electrons. So the final reaction is actually 2 Fe3 plus nickel will produce 2 Fe2 plus nickel 2 plus. Now if you look at this from a strict balancing standpoint and just try to balance the charge, I have 2 times 3 positive on the left, which is 6 positive, and 2 times 2 positive plus 2 positive on the right, which is 6 positive. So my charge is balanced, and I know that I've done it correct. That is the final reaction. So the element and charge is balanced on each side because they both have 6 positive. And that is my reaction. And I derived it from only knowing the reduction potentials. Now, if I want to find the electrical potential of that cell, I take 2 times the reduction potential of the iron, because there are 2 of them, minus the reduction potential of the oxidized side. So for the iron 3 plus electron becoming iron 2 plus, if I look that up in the table, I see that it has a reduction potential of 0.77. So I multiply that times 2. If I look up the nickel reaction in a table, I get negative 0.25 as its reduction potential. So if I take 2 times 0.77 minus negative 0.25, I get 1.79 volts as the standard potential of that cell, and it is spontaneous. One more example. Determine the standard cell potential to determine whether the following reaction is spontaneous. So here I've given you a reaction, but will that reaction happen? And I can answer that by looking at the standard potential. If the standard potential is positive, it will happen. If the standard potential is negative, it will not happen. Now the reduction potential of nickel is negative 0.25, and the reduction potential of iron 2 plus is negative 0.44. And if I look at this reaction, nickel goes to nickel 2 plus. Nickel is losing electrons. Lose electrons, oxidation, Leo. So nickel is oxidized, iron is reduced. And they both have 2 positive, so the charge is balanced. So if I did this, and I don't know if it's on the next slide, but I'm just going to say it now, I would need to take the iron value, because that's where reduction is occurring, minus the nickel value. And negative 0.44 minus negative 0.25 is going to give me a negative number, which means this reaction will not be spontaneous. So this reaction will not be spontaneous. From that equation, nickel is oxidized. So I take the electric potential of iron minus the electric potential of nickel, and I get a negative number. Since it is negative, the reaction is not spontaneous. Now, if I didn't even want to do all that work, I could have just looked at the activity series and I would see that iron is above nickel. Electrons will flow from iron to nickel, not from nickel to iron, which is the way this reaction was drawn. So it shouldn't happen. The check makes sense. So those were some examples. Let's talk about a prime example of the reverse of a voltaic cell, an electrolytic cell. The process by which electrical energy is used to bring about a non-spontaneous reaction is called electrolysis. Now I actually have an electrolysis set up for water, or I should say I used to have, I still have it, but it hasn't been working for a while, and I would usually demonstrate this and actually produce oxygen and hydrogen from water for you. So I apologize, you can look at some videos for how that works, but when you do it, you can make like little pops, little tiny explosions in test tubes out of the hydrogen and oxygen you make. But electrolysis is carried out against the flow. These are non-spontaneous reactions. We're going backwards. So we have to put energy in. So electrolysis is carried out in an electrolytic cell, one that uses energy to cause a redox reaction to occur the way it doesn't want to. The most common commercial electrolytic cells, just as other examples, and so that's it for the water one. I just wanted to let you know that I could turn water into hydrogen and oxygen by electrolysis. The most common commercial use of electrolysis is to produce chlorine and sodium hydroxide. Now remember, or if you remember that chlorine and sodium hydroxide are both really dangerous, but brine, which is basically salt water, sodium chloride in water, can actually be forced back into sodium hydroxide and chlorine gas. That's not the way it wants to go. Thank goodness, because if salt water spontaneously became chlorine and sodium hydroxide, we'd all be dead. But instead, chlorine and sodium hydroxide become salt water normally. But we can make this go backwards by adding electricity. So for water, 2H2O will produce 2H2 gas plus O2 gas. That's the electrolysis reaction I just talked about. But you can do any reaction backwards. And I couldn't get PowerPoint to do this, but normally you want that arrow to have electricity on top of it because it's acting as a catalyst for this reaction. So I just want you to understand electrolysis is when you apply energy to make redox reactions happen in reverse from the way that they want to naturally. Another common way of doing this is electroplating, and that's where you deposit a thin layer of metal on an object, and this is also done in an electrolytic cell. So for instance, you can copper coat things, and you may notice that that's like the common thing now. Everybody wants copper coated cookware right now. But all you have to do, you can make this yourself. You could take a piece of copper and put it in something like copper 2 sulfate electrolyte, stick whatever you want to copper plate in that solution, and then attach wires to it so that one of them is the cathode and one of them is the anode. And you can actually make the copper move from the copper anode to the cathode. The copper would actually come off and then replate on the other side. You can look up lots of videos on this if you're interested. I just wanted you to know what the process electroplating was, and if I had had time, maybe demonstrate it a little bit in class, but we won't be able to do that, so you can look up videos on that. So the anode is the metal, and the cathode is the object to be plated. So the electrons usually flow from anode to cathode, and what happens is, so the item to be plated is now negatively charged. So copper will become copper 2 positive, and that 2 positive will be drawn to the negative charge of the object to be coated. So you transfer that copper over. You take the electrons off of the copper so that it becomes C2 plus, Cu2 plus, and then you move those electrons to the object to be plated, and the copper moves through the solution and then gets plated on the object. The last thing, and since we won't really have time to go into the math here, but we do go into this in physics, which is why I just touch on it conceptually here, is the idea of electromotive force. When we talk about voltage, what we're really talking about is a potential difference. And we use that voltage to produce electromotive force. If I do 1 joule of work, when 1 coulomb coulomb of charge is transferred between 2 points, that's 1 volt. So 1 volt is 1 joule of work done when 1 coulomb of charge is transferred. I know that doesn't mean much since we haven't talked about coulombs or joules in chemistry, but I just want you to understand, in chemistry, is that there is this potential difference that's created, and we call that voltage, and that voltage can be done or used to do work. And I think that's the end of the slideshow.